Alrighty, welcome all to today's Passive House Alberta Building Better in Alberta webinar series, sponsored by the Alberta Eco Trust. My name is Frank Crawford, and I am the Education Committee Lead for Passive House Alberta. Today, Graham Finch, the Principal and Senior Building Science Specialist at RDH, will be talking to us all about building science and specifically the evolving needs of the building enclosures. But first, I would like to thank the Alberta Eco Trust for the ongoing support. It is very helpful in allowing Passive House Alberta to continue our work. As always, you can place your questions in the chat box and I will ask them at the end, or you can unmute at the end and ask him yourself. So without further ado, please take it away, Graham.
Well, thank you very much, and good to see everyone. A number of familiar names are on the Zoom here that I've chatted with in the past and worked together on. So it's a nice group here. We can chat about all the things that are happening in the world with related to building science and what's changing in terms of the way we're putting together our building enclosures, specifically wall systems. So just a bit of a, bring us all on the same page. What we're going to be talking about today is the building enclosure, and the building enclosure, for those that are in our industry, is doing a lot. It's a very technical aspect of the building, and it's controlling a lot of things, right? We've got to control water, condensation, airflow, both in terms of heat and moisture, contaminants, smoke, wildfires, the contaminants in the air, vapor diffusion, both a wetting and drying balance, heat flow, of course, insulation, light, solar radiation, noise, acoustics, and then fire, both the heat and also embers from wildfires as well. And at the same time, the building enclosure is transferring loads, from the cladding and from the wind and from all the loads the building is seeing back to the primary structure. It needs to be durable, maintainable. You need to be mindful of the materials we're using, especially nowadays, where they come from, what they're made out of, and of course, economical and constructible and look good at the end of the day. And most people might only look at the very last thing and say, that's a good building or not, right? And so for those that understand building science, we got to do a lot of different things here. And from a basic building enclosure perspective, we're looking at essentially that line that's drawn between the indoors and the outdoors that includes our roof, our windows and doors, our floor systems that are overhanging, walls, foundation on grade, floors, crawl spaces, separation of your garage, your skylights if you have them. So essentially the envelope of the entire building. And when we look at high performance building enclosures, there's just almost like a cheat sheet now. Is you can almost say that you need these things and you have a higher performance enclosure. And how high you go or how good your enclosure is depends on how far you push these different levers. But all high performance buildings will have continuous airtight air barrier systems, right? We need air tightness so we then can control airflow through the building enclosure, but then we also have mechanical systems that ventilate for us within our buildings. We need to insulate the above grade and also the below grade with the right amount of insulation. And that right amount of insulation changes depending on where you are, the type of building, the form factor, what your targets are. And there's sort of an optimal, and that's where we use energy models to optimize what the wall and the roof and the window performance values are. We want to minimize thermal bridging, so all the insulation we're putting in there is not thrown away. We insulate below grade a bit differently than above grade because of the contact with soil, and there's different insulation targets that'll be set up there depending on your foundation system as well and the details. The windows and the doors, you're selecting that glass and the window frame in conjunction to meet your balance of heat loss and heat gain. And then also consider comfort in that. And so Passive House and PHPP is really good at sort of looking at that gains and losses so you can understand how important those windows are and the sizing and where you place them. Skylights, if you have them, they are a hole to the in the insulation, but where you need daylight or want daylight and potentially benefit from heat loss and gain as well. And then when you're looking at carbon as it maybe a goal, then you're looking at lower carbon fuel source for high efficiency heating and cooling, typically heat pumps, plus mechanical ventilation with heat recovery. And the reason you're putting heat recovery on there is you're taking the heat energy that you're just pumping or blowing out, exhausting out from your bathrooms and your kitchens. And so you're recovering some of that energy back. And then if you're looking at and mindful of the materials, and if you have carbon goals, then you might look at the materials and use lower embodied carbon materials in your construction. So there's lots of these different parts, and the packaging of this what creates a high performance enclosure. Now, that's the performance side. The other aspect we're seeing more and more, and I think the biggest push for the next decade here is really going to be climate resiliency, and it comes in a number of different perils. We're all familiar with the disasters that are going on around us, but it's adapting those building enclosures so they aren't so easily damaged and actually can be resilient in the face of wildfire, flooding, hail, and high wind events. And so what does this mean? It's, engineering of that structure. So, if your windows and your cladding, and particularly your roofing for those higher loads or those potential loads, for the snow and the rain and what you're going to see. So it's a matter of just changing the inputs for the engineering. So that's pretty easy actually. Retrofit, then that could be a bit more work, obviously, but a new building, that's just day-to-day work. Selection of hail resistant and wind design roofing and cladding, so again, being resistant to hail events, hail resistant roofing, hail resistant cladding, where you have, places like Calgary and other places in Alberta where there's a real high likelihood of big hail events every year or so. And then redundant underlayments for water control. Location and siting for groundwater and flooding, trying to limit, where, putting buildings in those riskier locations, or if we are, then elevating them or elevating at least the critical components. It is possible to build in wildfire resiliency, and this is entirely, when you look at the building levels of building enclosure challenge, and there's landscaping issues and there's the larger forest issues, but when you look at the building itself, all the things you're doing for wildfire resilience are actually at the building enclosure level. In terms of your material selection and then your details. And so it's really a building science, like what are the assembly, what are the materials I need in there, and how do I detail for that? And largely it's keeping embers out of places it shouldn't go, and being resistant to heat. And then of course there's the landscaping protection around the house. So you can then use potentially less resiliency at the enclosure. So it's a sort of two-step. And then, looking at the building, overheating is another challenge that we're seeing in older buildings in particular, but, designing the building with cooling or the ability to put cooling into them in a retrofit or a new building. And then also we're looking at is, okay, how can you design buildings for power outages, whether you have backup or you just rely on the enclosure to be, well insulated. In terms of shelter in place and mitigating, freezing damage to water and other plumbing in your home. And then basement waterproofing and details and additional backup and water control. So these are the things that are being overlaid. Now they're actually being forced in by the insurance industry, and code is catching up to that. But there are a lot of places now you can't get insurance because of wildfire or flooding. And so people need to take, they really self-insurance where you're taking things into your own hand. And a large part of that is the enclosure. Now, while we're trying to do that, we need to look at obviously affordability, how we do this from a constructability and detailing standpoint, the performance, getting the right level of performance, as airtight as possible or feasible, and the right R value for, the actual design of the building, not just, guessing. Moisture durability and resilience there. So, all these things we can do, if it's going to rot away or get moldy, then that's really not, resilient and durable as well. So we need to make sure we're mindful of moisture, and then paying attention to the materials for embodied carbon and sustainability, if that's a goal as well. So from a building science perspective, what we do is we dissect, different building enclosure assemblies into what they're doing. And from a building science perspective, the building enclosure needs to control water, air, heat, vapor, sound, and fire. Okay. And so when we're doing that, we put things into the building enclosure in our wall, for example, a water shedding surface and a water resistor. So your cladding and then your house wrap, and that's there to control water. But your building form, your overhangs and other features, balconies, things like that, those also help to control water. So that's sort of tied in there. The air barrier system you notice in the middle here actually ties into all 6 control functions. The air barrier is there for air control, but it also impacts heat, of course, vapor flow, acoustics, fires is part of that as well, and also can help manage water. And thermal insulation, of course, is there for heat, but it impacts acoustics and fire. We have a vapor control layer or vapor retarder to control vapor. And then our building form features, as mentioned, ties into the water and the fire side. So when we're picking materials for that, we have a whole bunch of considerations for the material, right? What is it? Is it suitable for that application? Is it, moisture tolerant? How durable is it? It's that fire resistance properties, acoustic properties, the permeance, all these technical, material data that we have to look into to pick the right material to do these different things, right? We can't just use one material to do everything. I mean, you can in some places, you just put concrete and then you're done. But the reality for performance and achieving all these goals, then we need to mix a bunch of different materials together, right? In old buildings, one layer, truly did everything. This old stone church in Scandinavia, it was just stone. Stone came from the near the building, stacked up, and this has been around for 1,000 years or so. And one layer did everything. Now it's not that comfortable. There's no windows. It's missing a lot of things that we would require in a modern building. And that's why in newer buildings, we have control by separate layers and separate functions, right? We have a cladding layer, we have a membrane that's potentially, air, water, vapor all in one, or a couple of those, or one of those functions. We have insulation, we have, all the structure, we have all these different layers and they're all doing something separate. And so the whole building science is about putting the right materials together in assemblies and then detailing them together to hit that performance target. So, we all can appreciate, we probably grew up in a building that, was sort of built like this in Canada. If we grew up here, old buildings, they're either 2x4, 2x6 wood studs. You got drywall on the inside, maybe plaster if it's really old. You probably got a polyethylene air vapor barrier plastic sheet behind the drywall on the inside of the insulation. You've got some fluffy stuff of a different color. Maybe it's pink, maybe it's yellow. Bad insulation, providing insulation. You got your sheathing, whether it be OSB or plywood or old board sheathing. Maybe you got building paper or some sort of house wrap, and then you got a cladding. And your cladding might be hardy board, it might be vinyl siding, might be brick, right? So you've got these buildups where you've got, your water shedding, your water resistant barrier, your air barrier, vapor barrier, you got your insulation. So that's sort of what we start with. Now, when we look at older wall designs, especially in colder climates, we have challenges with that wall. Even though it works, we do have challenges with it in many different contexts. First is, that insulated wall, whether it be 2x4, 2x6, there's a fair amount of thermal bridging, which lowers the thermal performance, and you get discomfort, especially in really cold areas. You get condensation, if you put your couch or your bed right against that wall, you'll probably see condensation and potentially fungal growth and damage occurring to the finishes. If the air barrier hasn't been done properly, like this wall here, where the demising wall that run right into the exterior wall with a air barrier pre-strip there, you'll get condensation from air leakage, but also diffusion, which leads to fungal growth and decay. And then potentially you have rainwater getting in at a window or a roof to wall interface, resulting in fungal growth and decay. So there's lots of problems with this wall design, and we see it during renovations, we see it during rehabilitations or insurance claims. That wall's not perfect, right? And that's why it's ripe for betterment, especially as we go forward here. The other piece we see, and this comes up with the insurance claims, is, from a wildfire standpoint, that base wall is extremely susceptible to being combusted and burning down, allowing fire to get into the attic of the home. And then burning down the home. Hail, you see pictures all the time. There's hail events, vinyl siding just shredded off this building. And then the challenge here is it's going to take months, maybe years, depending on how big of damage or large area to get re-sided. And then that time, the water getting in the wall and then it's damaging materials that really can't get wet. Same with high wind, high wind events don't even need to be tornadoes, just need to be, really high wind events. Can rip, claddings off. It's not so much blowing buildings over, but it's ripping stuff off, right? And then flooding, and then the ease of drying and remediation after a flood event. And so these are the new things that we have to pay a lot more attention to, because we are being forced to by either insurance premiums or just lack of insurance or self-insurance. And so when you look at common wood frame wall modifications to address the performance gap, but also the resiliency measures, you start to see walls that might, be modified in some sort of way. So, if we have water management challenges, this is very common in British Columbia, but we're seeing the need here in Alberta and places as well, where water's just getting into bad details, and it really could benefit from improved water control. And the way we do that is we separate the water shedding and the water resistant barrier. We have a drained and ventilated gap that allows the water to dry out. And really, we don't worry about water as much anymore. We might add exterior insulation. There's all sorts of different types of insulation for improved thermal resistance, right? We might use a better house wrap for better air and water control. We might use some self-adhered, fluid applied, lots of different products so we can improve the wall and modify it. We can use different sheathing boards for fire resistance. We can use gypsum, magnesium oxide, lots of companies in Alberta that are providing alternates there. And as you know, with your codes for your sidewalk lines, you often have to do this. Alternate cavity insulation products, bat, blown, spray foam. And then there's alternate air and vapor strategies. You can buy not poly anymore, right? There's all sorts of different smart vapor retarders and other strategies there. So there's all these modifications that you could make. And what happens is their options are really endless in configuration and how you put them together. And this is where people get kind of stuck, because it's like analysis paralysis. Like, what should I do? I got way too many choices. Someone's trying to sell me this. Someone's trying to sell me that. How do you cut through this? And this is where we use the building science to sort of evaluate these different options to say, okay, this is as a designer or a builder, this is a good way of building, or this is maybe a not so good way. Now, it's important to realize that building science never changing, right? We know more, we're learning more different things, but so it's not changing. The physics aren't changing, but the requirements and expectations for enclosures are changing. Public, what people expect from a building performance in terms of comfort is way different now than it was 50 years ago. And there's also a change in response for evolving climate, just different loads, the consumer, and then the insurance. And the insurance industry is probably going to be the one that hits us home. So what are the new expectations or requirements? Well, there's more thermally and energy efficient buildings. That's just based in, more stringent codes and consumer expectations. So the codes, raising the bottom, and consumers are actually from the top saying, I want this in different markets. And it's not everywhere, people still value, cost obviously, but there really is this push towards more thermally efficient homes wherever you are. More resilient, right? More resilient into what, right? And there's what are your local perils? You got the wildfire region, or exposure, flooding, hail, wind, water, climate. These are design inputs, and of the insurance industry and the consumer expectations here are pushing that. And then the third is mindfulness of materials. So this is consumer driven, but there's also codes and guidelines that are looking at embodied carbon that are coming into place in different regions to saying, okay, here's what the maximum, embodied carbon or operational carbon might be. So these three drivers are changing us from the way we're currently building, and we're having to adapt. So what does it mean though in the end? Functionally to achieve all three of those at the same time, more airtight, better insulated. And I say better, just the right amount of insulation. Doesn't mean super insulated, it means the right amount of insulation for your target. Mindful of materials, right? Especially now, use Canadian, right? And then are more resilient to local hazards. So knowing the risk and then how you adapt the design to that. And so, NRCan and others, they're developing tools. You can put in your address, your postal code, and it'll tell you the risk of different perils in that region. And you can say, okay, I'm going to design this house for these events, or maybe I will consider wildfire resiliency in the building. And so what we'll end up with is something that's truly future-proof and sustainable, and probably never needs to be retrofit ever again. So how do you go through the science of this? So the way we use building science is we use control layers to slice and dice and evaluate different designs. So I'm going to walk through a couple here just to sort of walk through it. Okay, so in each of these walls, I'm going to identify water shedding, water resistant barrier, air barrier, thermal insulation, vapor retardants. There are control layers that we're putting in there to control these things. Okay, so if we look at our baseline 2x6 wall, you've got cladding right over house wrap. Your insulation is your wood, or sorry, your bad insulation. It's bridged by bridged by the wood framing. You got air control, which is taped and sealed poly. You've got vapor control, which is your just having the poly there. So that's your base design, right? That's where we're all maybe comfortable seeing it and building. Now, you could do different things to this. You could use different air barriers. You could use spray foam. You can use airtight drywall, whatever you want. So as we look towards improved water control, right? If we're seeing, you know, the climate's going to tell us, or the building design is going to tell us. BC learned really hard 30 years ago that if we built buildings certain ways without overhangs and really bad details, then we're going to need to change the water control. And we're seeing this in Alberta too. We're seeing a lot of claims. You know, BC, it took 5 years for that, and Alberta takes like 10 to 15 years, you know, for if you have a really bad detail. So improved water control, rain screen. What is a rain screen, right? You separate the water shedding from the water resistant barrier by a gap, right? You leave a gap between the two layers. Any cladding manufacturers already require this anyways. And so we're already being pushed in this direction, and it's just simple to do. And most people building high performance homes are actually just doing this as a matter of course, even if you don't have to. You know, the insulation is the same, the air control is the same, the vapor control is also the same. Okay, so all you're doing is changing the exterior water control there. As also, of course, you can do all sorts of different things as well. Now, as you need to, you know, hit higher R value targets, we're also probably pretty familiar with adding exterior insulation. You know, in this case here, we're adding exterior insulation. We got the good water control on the outside. We've got a rain screen. In this particular wall here, we're putting a WRB behind the insulation. We can also put it at the face of the insulation. Right? We have some choices there. As long as we do one, then we'll have, you know, decent performance. But if we don't, you know, if we just hope for the best, you know, that's where problems happen, right? And now thermal control is obviously improved. We're adding insulation to improve thermal control in this case, and so we get better R values. The air control can stay the same. The vapor control could stay the same, or as we add exterior insulation, this is where we start reconsidering vapor control and potentially air control. Okay. Now, there we also, instead of doing exterior insulation, we could do a double stud or interior insulate. You know, maybe have our good water control there again with the rain screen. We add some more insulation on the inside, put the air control here and the vapor control there, or we could move it to the inside. So we have choices, right? We could move things around, and we can use the building science to assess these different assemblies. So that's one way of sort of path forward to higher R values. If we need even higher R values, we can make that wall even fatter. Again, doing the same thing for water control on the outside. We just added more layers of insulation in deeper cavities. We have to look at air control and vapor control. In this case here, we're putting it towards the inside. We could move it around. We have choices there where we put those materials and what those properties of materials are. So there's different ways to sort of, you know, skin that cat, so to speak. Now, as we go on the path for thicker exterior insulation, there's a number of reasons that people are using exterior insulation for higher values. You start building that way, it's just adding inches of insulation rather than, you know, framing out deeper walls. And there's also the path for commercial assemblies that are using steel or concrete or maybe mass timber. And so we see the commercial market, you know, all exterior insulation and really not doing the fatter walls just because of the construction materials, and the residential industry doing a bit of both. And so as you add, you know, more insulation, you know, you look here, use longer screws for that insulation. The water control is the same, but the magic, you know, sort of about this too, as that gap gets bigger and we're separating the water shedding surface further and further away from the water resistant barrier, it's harder for water to get there, right? So that also improves some resilience. We got better thermal control. We got less thermal bridging impacts with the, you know, exterior insulation. The air control, when we start thinking about this, might shift from the inside to the outside. The vapor control also needs to be rethought, and we often will shift from, you know, say poly to something that's more permeable, and then we might, if the ratio of exterior insulation is high enough, we just put this on the outside. And so when you look at a wall like this with, you know, maybe 3 inches of exterior insulation, you know, you might have a smart vapor retarder on the inside. But once you go, you know, 4 or 5 inches, then you got enough insulation on the outside that you don't need a vapor barrier at the inside. The vapor barrier, the vapor control function is being managed by that OSB or a membrane on there, or the ratio of the insulation or the foam insulation. So you're shifting things towards the exterior, and now shifting the vapor control towards the outside, and then the air barrier might be placed behind the insulation there as well. So we can evolve that sort of design and we can go thicker. Once you've got more than half of your R value, the nominal R value of the exterior to cavity insulation on the outside, then you're shifting that air and vapor control to that sheathing level as well. You're not putting it on the inside anymore. So the air control, vapor control that you're sheathing, the air control might be a house wrap there, might be the sheathing itself taped up, proprietary sheathing products there. And then your vapor control is actually just managed by that insulation. Okay, so the thicker insulation shifts the control layers towards the outside, and you go even thicker as you need to hit higher targets depending on what your goal is. Now, when we're looking at the same, looking at that sort of the insulation sort of pathway, when we're looking at wildfire resilience, one of the things we're looking at is fires from the outside. So now it's combustibility, the cladding. So the cladding combustibility is important. So we want to use non-combustible materials. But foam plastic insulations on the outside also melt. And so when we're looking at wildfire resiliency, we're protecting that foam or we're changing that foam to something else. And there's a building actually in Jasper at EIFS. It was retrofit at some point with EIFS. You see the styrofoam there. And the heat from the fire melted all the insulation. There's basically nothing left in the cavity here over the old stucco home. And because it was stucco, actually, the fire wasn't able to get through here. So the house was actually saved in the fire. So a good result. But we can do better than melting insulation there if we want to protect this. And so what we were seeing being done is you use a non-combustible and fire-resistant insulation. And this is mineral wool. Generally, so it suffices for this. It provides insulation, but it also provides wildfire resilience. And then you pair that with the details for ember protection and your cladding attachment so that in a wildfire event, this will all stay in place and that insulation will actually insulate the rest of the home there. You can also put mineral wool over foam plastic insulation to protect the foam plastic insulation as another way of providing that resilience and that rating, essentially, so to speak, from the outside. Now, when you look at the code for exterior fire ratings for walls, and you've seen this probably in like Edmonton and Calgary and places where you require for sidewalk lines, you require gypsum, essentially on the outside of a certain minute rating. You can also achieve that same rating with using mineral wool on the outside. And we've done some testing recently for sort of wildfire resilience looking at this. We got one wall with mineral wool on the outside and one wall with gypsum, just to sort of look at the difference. One gives you insulation, one just gives you fire protection. You're getting insulation plus fire resilience here. So, so you're getting an extra thing. It's more expensive, of course, but then you got that benefit that might provide. This is the wall being tested here. Is a pretty high intensity wildfire load at the base of the wall, fiber cement cladding. You can see it sort of, gets discolored there. It's getting quite hot, cracks a bit, but it's largely intact actually, and somewhat salvageable. Reside certain parts. But the neat part is you look at in the rain screen cavity here, the wood furring here, untreated, just regular wood furring, is a bit charred. Didn't combust through there. The insulations, looks a little bit burnt there. You can look at its, impact is sort of the outer layer. The magic and the crazy thing is the house wrap, and Tyvek and the tie partner house wraps, those get up to like 80, 100 degrees Celsius and they start to melt away. And what we found here is just that couple inches of mineral wool protected the house wrap. Even the fasteners for the cladding, the metal fasteners for it didn't even melt a hole. So the neat thing about this is you actually get resilience because you can just rebuild the house without it, having being complete loss. And so you don't have to redo all the house wrap. It's there, and then you just replace the insulation. So this is a way that you can add resilience with insulation. Similar wall, this one vinyl siding with gypsum, and this one here. The gypsum protects the wood. You can see here the wood was fine, but then the house wrap's all toast, and then in this case we had vinyl, so it also wrecked the furring there. But you can see again, this is what gypsum is doing on the outside of that wall. It's also protecting the wood from that fire going through. So you have options, right? And these sort of resilience options, and you have choices there in terms of improving that wildfire and exterior live fire resistance. Now, when you look at insulation options, there's lots of different options for insulation. And what we look at, okay, there's different densities for how you attach the cladding. You got vapor permeance, whether it's low or high perm, air permeance, and we're looking at there is whether it can be an air barrier or part of the air barrier. You got to have a separate air barrier. Combustibility, moisture tolerance, fungal growth risk, and foam plastic, mineral wool, fiberglass, they're all really resistant to moisture. Whether for exterior applications, low risk from fungal growth. But what we got to watch is if we're using, say, a bio-based insulation, whether it be made from wood fiber or hempcrete or other sort of organic materials, mushrooms, whatever. Those have a very different moisture tolerance and fungal growth risk. And so we might need to protect those insulations a bit better than we would traditionally protect, say, foam plastic insulation. And then we got to look at the water repellency, the drainability, and other environmental aspects. So there's lots of choices we have with exterior insulation in that exterior insulation wall, and we're going to choose a type of insulation depending on our project needs. With exterior insulation, cladding attachment is narrowed in as one of the first, sort of problems to solve. You can screw right through exterior insulation, create essentially a truss with long screws. Lots of testing on that resources that can make available. It's pretty straightforward, but in the commercial sector, there's all sorts of different clips and ties and other components that are entirely made for this application where you're trying to reduce the thermal bridging through your exterior insulation and then attach whatever cladding you want on the outside. And we can go up to a foot, even 16 inches or more with different clip systems or long fasteners and lots of projects examples. And it's a fairly easy problem to solve that initially the industry was quite concerned about, but through time and engineering and projects, it's quite straightforward. So nowadays on the market, there are dozens of different systems. They all have different ways they're installed and performance attributes. The key thing with any cladding attachment is use as few as possible to save money, and then optimize them thermally and structurally. So this is one of those value engineering where using less saves money, better performance, and if we get the structure right, then we got the right amount of meat, so to speak, in there. The other shift we're seeing towards, especially driven by carbon, we're seeing more and more people looking at bio-based insulation. So going back to our roots and making insulation out of straw and hemp and wood fiber, seaweed, depending on where things that we used pre-1930s, and we're bringing back in modern form. These products are all more moisture intolerant, you could say, than say foam plastic, right? So that you can put stuff in them, you can put new additives and lime and borates and other things like that, but they are still more sensitive to moisture, and they will always be more sensitive to moisture than the products we're probably used to using. And therefore we need to keep water out of them. And whether we use some sort of coating on the surface or just put the house wrap on the surface, it's the easiest way. That's what most people are doing right now, is put the house wrap outside there. Protect that wood fiber, and you go away with it. The thermal control, again, you got to watch humidity levels in some of these products. We need to make sure that we don't end up with fungal growth there. In climates, like most of Alberta, generally pretty safe to use products like this. Where more of the concerns come are really wet, high humidity places like coastal BC. But we're able to use those products here with just being careful not to dump water into them, or a lot of water onto the surface of them, and they'll do just fine. Air control, all we're doing is changing the insulation, maybe in the cavity or on the outside. So the air control, the building science is the same. Be on the inside, be on the outside, can be combined with that product potentially. And the vapor is also the same as before. Now, one thing with vapor control, you just got to watch the humidity. So if you have diffusion going through, we need to make sure it also get out. And so when you're looking at bio-based installations, people tend to be a bit more cautious with dampness and letting things dry out. And so we don't trap water in seasonally, say, at the poly or something like that, if it's a wood-based insulation. Bit of moisture in fiberglass for a few weeks, it'll dry out. A bit of moisture in that wood fiber will dry out, but it could lead to mold growth in that period. And that's what we're trying to hedge against there. So the building science is all there. We're just changing the materials, and as long as we're aware what we're tweaking and changing and then adapting, then we're good. So we're seeing these shifts wherever you are. There's different drivers all across Canada and the US. The target is being, the minimum code target is setting that sort of baseline. And then consumer expectations are bringing it up. And then we have programs like Passive House, Net Zero that are, sitting there at the top that are helping people, and the code's eventually going to get there. And then people are eventually all going to be building, Passive House level of, very high, net zero sort of level of performance at some period of time in the future. We need to build more resilient, and that's driven by consumer expectations, but also insurance requirements, whether it be self-insurance or getting insurance or the ability to get insurance by having to do these things. That's being driven there as well. We're being mindful of materials, and this may come from the consumers or it may come from the bottom up or top down. And so it'll be a bit of both. And that's looking at the embodied carbon. And what that's doing though is you're getting these different alternate materials, but the other materials that we're used to using, the foam plastic, the mineral wool, concrete, all these materials, they are becoming better, right? So actually having those drivers at the bottom means all these other materials actually get better in terms of, sustainability. So, in the end, or we end up with hopefully better materials. We got to, watch things. We don't have unintended consequences, but that's sort of an aside thing that you can also look at. And so this is why we, use building science. So building science is that tool to evaluate your options and make informed decisions on suitability and risk, and help you dissect and really slice and dice what you're doing and understanding what all those different layers are really doing, and then the risk on our designs. So lots of neat things ahead. Of course, more change. Some people don't like change. Some people do. So embrace it, or, hire someone to help you out.
Excellent. Thank you very much, Graham. Yeah, lots of new interesting things, and yeah, resilience and insurance is it's going to be one of those new drivers that's gaining in importance. All right. I have a bunch of questions, but before I start asking all of mine, I don't see any in the chat box, but if anyone wants to unmute and ask a question, by all means, do so. All right, I'll just start asking some of mine then. So you talked a little bit about the insulation interior and outerior, inside and outside the vapor control layer. So in Alberta's cold climate, roughly how much exterior insulation do we need to be able to move that kind of vapor and air control layer all to that same sheathing layer, which then things get a little more simple.
Yeah, so there's like the old rule of thumb was if you put 2/3 on the outside, 1/3 on the inside, then you're generally pretty safe to do something like that, right? So if you had, a 2x4 with all R12, and if you had R24 on the outside, that's 2/3, 1/3, right? Now give you R36 nominal and 30 or so effective. That would be quite safe. Now, what you find is that ratio depends on what the indoor use of space is and the humidity, right? So if you're in a commercial office space, very low humidity and a lot of moisture generation, you don't need 2/3. You probably get away with less than 50%. And so the indoor use, lower humidity means you can use less exterior insulation, whereas higher humidity. So if you're doing multifamily, maybe social housing, where you have higher density and maybe less control over the humidity, then you need more, right? And 2/3 is probably pretty safe there, maybe down to like 60, and you can use models to sort of assess that. If you look at pools and they're sort of high humidity spaces, then you really shouldn't use any interior insulation. It should be all exterior insulation. There's be no shortage of pool and museum failures in Alberta to remind the industry of that. So, once 50% humidity in Alberta pressurized is a good recipe for disaster. We see a lot of projects that have tried to do that, and it's not good. And so that's why all exterior insulation in those types of buildings.
Yeah, excellent. Thank you.
It's definitely a continuum, and you're using, that insulation to shift the vapor control, air control the outside. But the riskiest wall you can actually build is like 3/4 inch of like foil faced ISO on like a 2x6 wall with poly, because there's not enough exterior insulation. You got vapor barrier on both sides. Any water, air leaks get in there, then you're trapping it. And those are the walls you don't want to build.
Yeah, stay away from those double vapor barriers. It's interesting you showed the mineral wool on top of foam or anything. So is it like 1 or 2 inches of mineral wool and basically we are fire resistant? Like obviously there's some
Yeah,
code things in there, but
yeah, an inch
roughly?
and a half, 2 inches is sort of being what's looked at. There's a few companies that have done, like Suprema did a bunch of testing where they put, they did the high rise facade test, and they had like 2 inches of mineral wool and like 8 inches of polyiso behind it. It seems to be it's really like a melting point of that insulation, but like 2 inches is generally enough to get you that sort of protection on the outside. Now, of course, if fire or flames can get around, right, at window heads and things like that, that's where the weaknesses are. So, and that's what you have to pay attention to in the detailing. So we are seeing that sort of hybrid in the commercial sector. And the one driver for that is like, polyiso is like R6 per inch if it's cold temperature, polyiso, not, older technology blowing agents, but, that's, quite a bit better than the R4 per inch that you're 4 bar or so you're getting for mineral wool. And so you put, the higher R value insulation behind the protecting insulation.
Okay. Anyone else want to jump in? If not, I'm just going to keep talking.
Mhm.
Um, to follow up, so there polyiso that maintains its R value, like the new types?
Yeah, if you look at the new blowing agents that, Suprema is one example, Canadian company that's making it. Their polyiso, their Silver ISO Plus, I believe, has a cold temperature curve that is quite a bit higher. Dow Thermax, or DuPont, I should say Thermax. Now, there's also you just got to look at the manufacturer. Like the Canadian focused companies have products now. If you're buying a commodity American product, then you might not get the same performance out of that.
Excellent. Yeah, just ask for the temperature versus R value curve, and yeah, make sure it
Mhm.
doesn't crash. Um, Another question on the rain screens. What's kind of your recommendation for a minimum thickness of rain screen, and then maybe what material you're using for that strapping to add some of that fire resistance?
Yeah, so from a rain screen standpoint, I mean, you can put any cladding on a rain screen. I think it's important to realize you can put any possible material on a rain screen. Even stucco, you just got to put a backer for it, right? Um, so any material, and from a gap standpoint, a very small gap. Like if you look at the U.S., like you put 2 layers of like crinkly house wrap together, you can get drainage. You just don't get ventilation. To get drainage and ventilation, which you want in a rain screen, you need about a 1/4 inch. And so what the industry's done is like went to 3/8, right, or 10 millimeters in the code. And so because it just tolerances, right? Like if you put just a 1/4 inch in there, it might be fine, but then you start getting peel and stick and other buildup, then you start closing off. So 3/8 is a good, you know, 3/8 plywood is pretty readily available, or you just rip it into your strips. Most of the commercial market uses like 3/4, maybe an inch. We try to keep it less than an inch because if it gets bigger than that, then you can get fire spread within that cavity. But if you keep a rain screen less than an inch, you don't get fire propagation because there's not enough oxygen coming in. It's like a chimney that you've really flattened down, right? So your flue's not open enough, and so you keep the gap small enough but big enough to let the direct water and air flow in there, but not the flames of that fire. And in terms of strapping, like when residentially, most people like nailing things, so they'll use wood strapping. But if you're screwing things, then you can use metal hat tracks or Z shapes, or plastic. There's all sorts of different components that have been invented. But the simplest is just ripped plywood. You can use treated plywood if you're a wet environment. You can use fire treated plywood if you want some fire resistance. What we've found is those furring strips are a pretty minor element, and you may not need those to be non-combustible for if you have a non-combustible cladding. But if you do have combustible cladding, then it would make sense to use something that might be a little bit better there. And then, yeah, put that through the exterior insulation.
Excellent. Thank you.
See some
Question.
questions now. Yeah.
Yeah. How would you build a wall system to protect from both wildfire and hail in Alberta and roughly an R40 wall?
Yeah. So, um, R40 you could do with, like you probably start with 2x6 wall, and right, so they got R16 or so effective, so you need another 24 or so effective, right? And so if you need 24 or so effective, let's call it 30 nominal, that's like 5, 6, 7 inches of exterior insulation. So one route is put mineral wool on the outside, and that would give you the fire resistance. The hail resistance is coming from your cladding, right? So it's cladding that can take the abuse and then be tested against hail. So, fiber cements, high pressure laminates, different types of boards that are made that have some hail resistance. Metal can be if it's thick enough, but if you have lower gauge, lighter gauge metal, as you say, and the hail's hitting you, you're going to get dids, and then you might not like this is like your car hood, right? So you might not like the look of the dids. So then metal might be off the table there. Stucco does pretty well, and this brick, of course, does really well in that application. Now, if you didn't want like 7, 8 inches of exterior insulation, you could just put 2 inches of mineral wool on the outside of that wall and do a double wall or a deep wall on the inside. So you could put, R8 or so on the outside, and you could put 32, effective on the inside, which is probably like R40 worth of insulation. So it's probably a foot thick wall with 2 inches on the outside if you look at the actual effective R values for something like that. It's sort of an option. So you can do inside or outside. But what the key thing for hail is the material on the outside. The key thing for fire is the cladding plus that insulation. Or you could use gypsum too if you didn't want that extra insulation. And of course, details. And there's a bunch of NRCan resources on this right now that sort of look at wildfire resistant construction details for like how you screen rain screens, how you detail soffits, whether they're vented or not vented. Lots of different ways to do that.
Thank you. All right, another question. What would you recommend as the first step to improve a traditional basement system for thermal, vapor, and air control layers? If building high performance, going, I guess, yeah. How do you get some high performance without too much cost?
Yeah, I mean, this is newer renovation.
I don't know. Sean, do you want to do? Is it retrofit or a new build? New build.
New build, ICFs. ICFs, if you can. I mean, if ICFs are too much, then if you can try to get at least a couple inches of foam on the outside, or if you want it, but typically people would put styrofoam on the outside. That 2 inches, like R10 on the outside of your foundation, will keep that concrete significantly warmer and drier. You could put batt insulation on the inside of that. You might not need to. If you can get even a bit more foam on the outside, then nothing on the inside, right? Just put the drywall furred off the concrete and whatever space you need for services there. But with a basement, if you can get insulation on the outside, then you address moisture, you address a whole bunch of other things. In a flood event, you can more easily dry that out, especially if there's no bad insulation in there. So if you're in a flood environment, then maybe not use paper face drywall, use something that's a bit more resilient, and then easy to if the flood happens, cut off the bottom of the wall and then dry off that cavity. So it depends on what you're sort of building towards there.
Excellent. And I guess why don't we ask the same question if it's a retrofit? And I think the answer is probably similar, but if we have an existing concrete wall, what are the retrofit options?
Yeah. I mean, if you're not digging out on the outside, like some people will be digging out new perimeter drains, they might have to for municipal reasons or because they have water ingress issues. So if you're doing that, put the insulation on the outside when you backfill. That's easy. If you aren't, then you're looking at interior insulation, and that's where like closed cell spray foam works really well, right? Against irregular concrete, stone, rubble, concrete block foundations. If you don't want to use foam, then you can use, mineral wool with a smart vapor retarder on that as sort of the balance for letting, controlling vapor, and air, but also allowing some drying. What we know doesn't work is just bad insulation and wood studs and poly. That recipe results in lots of problematic basements with water gets in, gets trapped, or air leak gets out, the water gets trapped, and really poorly performing basements. So if we just shift the insulation to the outside, then the performance problems all go away. And ICS new buildings, just it's like one and done.
Yeah, excellent. Are we, I guess, talking a bit about embodied carbon, are you seeing ICS being able to either use lower embodied carbon or get down to 4 or 6 inches of a concrete core, or are we still kind of stuck at the 8?
Yeah, I mean, unless you have an engineer sort of looking at it carefully, but I mean, you can always engineer thinner concrete. It's just within reason, recover and everything else. But yeah, that's why we're seeing people look at the embodied carbon of the concrete itself, right, and the production there, the cement, and then seeing aggregates and things like that. But that's one of those things where concrete is, one of the best materials for that application. If you really couldn't use it, like, we see a lot of industry you do in North Alberta too, but if you don't have access to concrete, people will build with like PWF or pressure treated wood foundations, right? It's another alternate to that. So we see lots of cabins and islands and things here that there's no concrete, but you need a basement, and that's built out of plywood and treated wood. And of course, that be more moisture sensitive needs, the insulation needs to be on the outside there as well. So concrete, you use the material as much as you need structurally and optimize that. And if you really are trying to get away from carbon, then you could look at wood, but then you really got to protect that with other materials. So you got to sort of do the life cycle trade-off on that.
Yep. All right, so a longer one from Ethan here. When building a super thick double stud wall assembly with at least 2/3 of the insulation outside of the interior framed wall, what would be a good product to use as your vapor control layer on the outside face of the interior wall?
Yeah. I mean, Alberta has lots of experience using poly there, but the challenge with poly, um, you could replace that poly with a reinforced, different modified different plastic smart vapor retarder, yeah, Intello, Siga, Certainty, products like that. You just got to watch the permeance of that. You do need a vapor control layer there for sure, and you definitely need an air barrier as well. So you do need something. And if you got to careful where you push this, because if you're pushing it further out, the humidity is higher, and then those products will be more permeable than you do think they are actually. And so you want to put more towards the inside. That's why the 2/3, 1/3 are good. Honestly, really like using 1/2 inch 3/8 OSB or plywood. It works really well. In that application, it's rigid, but you can also use a membrane. You just got to be more careful with the membrane. It's more suited to people that are more careful doing this type of thing than some builders.
Yeah, he's listed a few vapor or smart vapor membranes, and yeah, those would all work.
Yeah, you do have to watch smart vapor retarders in double walls if you start shifting them out, because they're in a more higher humidity environment, and therefore they might not be one perm, they might be like two, which might be fine. It just, you need to watch that.
Interesting. So a question about, have you heard of board insulated sheathing, which is some are made in Alberta. I guess another product we could look for foundations as the SI construction, which is kind of foam and steel stud foundation wall. So again, the structure's on the inside with foam on the outside. Have you looked at some of those other, I guess, more innovative, new, less standard construction options?
Yeah, I mean, with anything new, you can again take it, cut it apart, slice and dice what things are doing, right? So like any of these steel and foam things, panels, and there's lots of them, and then there's some really good products in that sector. We've used a lot of them. Is what are those different materials doing, right? The foam is often your vapor control layer. If you seal the panels with something reliable, that can be your air control. Water control is where most of these products would have challenges, right? You gotta watch how they come together. Any panelized thing needs to be sealed, probably on the inside and the outside for air and then water control. And if you're just sealing one side, you really gotta watch, can air get in there or water get into that? And so it's all about the connections. These insulated sheathing boards can work quite well. The challenge is if you use the thinner ones, it's not enough insulation to really change your vapor control on the inside, or you're kind of creating a double vapor barrier there. And so thicker is better, right? So I would love to see more of these insulated sheathings that are like 4 inches of insulation rather than like an inch. An inch is, it's, if you look at an inch to 4 inches, yes, there's a cost to that. But like the benefit that has, especially for a lot of projects, is like you're doing all that effort, put a bit more insulation and really future-proof something like that. And so, a lot of people will be stuck putting like a little bit of insulation. You're like, oh, you're so close yet, so far from where you need to go. So use more.
Yeah, it's cold here. Things that work in the southern states and stuff don't always work in Canada.
That's right. Yeah, yeah, and a lot of them are American manufacturers, and yeah, an inch and a half zip sheathing and stuff like that's totally fine for most American markets, but Alberta is different, right? So it's cold.
Yep. All right, we're getting near to the end. Any other questions? Look through the chat box. I think we got them all. Yeah, I think we covered lots of good ground, lots of good kind of general stuff, and then some really interesting details that we love to dig in on to. So thank you very much, Graham. Last call for questions, and if not, yeah, we're done a few minutes early.
Great. Thanks, everyone.
Thank you very much.
All around.